Okay, so everybody, welcome to this talk on the theory of relativity and possible alternatives where you might actually be able to travel faster than the speed of light. So Einstein had the idea that there was a limiting speed of light and lots of other stuff. Now I'm going to be talking about how things might actually be different, how the speed of light might actually not be the barrier that it's made out to be. Now I can't really prove this in this particular talk, but rather illustrate the possibility. Now I'll give a brief outline of what I'll be talking about and then I'll get into it. Now relativity emerges from a progression. You might not realise it, but it actually comes from electricity and magnetism. So we start off with charges, and then we have electricity, and then we have magnetism leading to motors and generators. And so these ideas were sort of kicking around, and it was this gentleman here, James Clerk Maxwell, who actually brought all those disparate theories in electromagnetism together, and he did actually explain radiation. You know, even these light from the lamps above us. You might not think about it, but light, radio waves, gamma rays, X-rays, all cut from the same cloth, all radiation, and it was this gentleman who was the first person to bring those things together and say, hey, you know, this is the story behind radiation. It's actually electromagnetic. This particular theory did, however, have some residual problems. And here's the gentleman, Lorentz. Lorentz, now he did fix these things up, but he did it in an unsatisfying way. There's a lot more to it than that, but that's the best description I can give at the time. Then, of course, the next person was, in fact, Einstein. Now, he's talked about stuff about the speed of light being a limiting value and came up with relativity as we understand it today. I'm going to be going back to electromagnetics and outline that Maxwellian synthesis and its problems and how they were fixed by Lorentz and Einstein. But then, though, I'll be looking at an alternative of Ritzian Electrodynamics, and this is Walter Ritz, who was a Swiss physicist who was actually working on an alternative to Einstein's theory of relativity. Unfortunately died early. Now some people say that his theory wasn't that good, but you could equally say if he lived a bit longer, maybe he would have been able to advocate for his theory. So I believe that this gentleman did actually come up with an alternative not just to relativity, but Maxwell's theory, one that didn't need the Lorentzian fix and didn't obligate relativity and was able to solve the conundrums of physics along the way. Now, after looking at electromagnetics, we'll then look at light, relativity, the claimed speed of light and some related issues. I'll then start to look at how light might not be a limiting speed after all, looking first at cannons, so there's our cannons, and then rockets, electron guns, exploding cannonballs, throwing balls from the back of a moving truck, and then exploding or decaying particles, and an experiment I came up with to actually shine some light on the picture. Then, considering how things might break the speed of light, we'll take a look at interstellar or astrophysical jets. They are things that seem to be travelling faster than the speed of light, while a relativistic interpretation would say that they only seem to be travelling faster than the speed of light. Now I take issue with that, suggesting that they're really moving faster than the speed of light. Lastly, I'll have a look at another piece of claimed evidence for relativity, atomic bombs. And I have to show you that the supposed evidence for that connection is actually more rubbery than you might think. And after that I'll close things, though there is indeed a great deal of related issues, and to be sure I can only fit so much into this sort of general talk. So anyway, let us go to electromagnetism. Now there is the story of the comb, you know, combing your hair.
Today I'm going to show you a fun little static electricity experiment, and all we've got are some little bits of paper. They've come out of a hole punch, those little circles of paper, and we've got a comb. So what we want to do now is comb that comb through my hair. Okay, there we go. Just combing the comb through my hair. Let's see what happens when we put it
now,
near the
notice how the bits of paper are attracted to the comb and then they're also repelled from the comb.
And attach themselves,
right, if you look carefully,
to the comb.
So they are. You can actually see both attraction and repulsion in this particular experiment.
So there we go, the static electricity.
That's part of the picture about how electrostatics
built up on the comb
works.
attracts the bits of paper, and they stick to the comb.
Now, the next part of the story is this is what was called Coulomb's law. Now, this basically it's putting a mathematical flavour on that picture that I just showed you. Notice the two blue things are charged positive, they repel. Like charges repel, according to Coulomb's law. Unlike charges attract. You can see the second row. I wonder I'll even try to do that. There's the second row, so unlike charges attract. And you can see there's actually a formula here which says the force between them, we multiply the charges and we divide by the distance between them squared. So that's, I hope that's making sense. I'm trying not to overwhelm people with formulas, okay? People are laughing, but never mind, I suppose that's maybe part of the picture. So what did we have? We were combing our hair, we had charge, we had positive and negative charge. The next thing to keep in mind is that charge in motion is electricity. So that's the thing that is travelling through the wires. It is charge in motion. Now if we go here is also the fact not only is charge in motion, but when...
Charge in motion.
Charge in motion is electricity. So here's a wire with electricity provided into it, and it generates a magnetic field which makes that compass needle move. So the thing is, electricity causes magnetism. You know about electromagnets. Is electromagnets a concept for people here? Well, you'll have to take my word for it. Electricity flowing through a wire generates a magnetic field. Normally we don't notice that because of a very small electric field. You need a lot of wire and probably need a metal core to make the electromagnet work. But the flow of electricity causes magnetism. So that's some of the things. We have charges. Moving charges are electricity. Electricity generates magnetic fields. Now, magnetic fields lets us do some other things. Okay, there we are. Now, there's a motor. So the electricity generates a magnetic field. The magnetic field pushes against these permanent magnets and we have a motor. Now, and the next one. Okay, now here is the turbine hall with the Snowy Mountain scheme. So we're talking about generators. And again, here is a generator. It's saying that if we have a changing or a rotating magnetic field, that will actually make current flow in a wire. So this is the principle behind a generator, right? Changing magnetic fields make current flow. So now there's also a gentleman here who is illustrating this with some coils of wire.
I am going to demonstrate electromagnetic induction with an experiment similar to the one that Michael Faraday performed. I have an ammeter here and I have 3 coils. I have a coil with 1 loop, 10 loops, and 100 loops. I also have a bar magnet, and I will start by connecting the single loop coil to the ammeter. I now have the single loop coil connected to the ammeter, and I'm going to move the bar magnet into and out of the coil. And if you watch very closely, you can see a slight deflection of the ammeter needle. Okay, so now let me connect the 10 loop coil. And then I'm going to do the same thing. I'm going to move the bar magnet in and out of the coil. Now you can see more movement of the needle. In fact, if I go very slowly, you see just a little bit of a deflection, and if I go quickly, you see a greater amount of deflection. Also, as the magnet is going in, the needle deflects to the right, and as I pull the magnet out, it deflects to the left. But when the magnet isn't moving, there's no deflection, indicating no current flowing. Okay, so when the magnetic field is changing going into the coil, there's a positive current flowing. When it's changing coming out of the coil, there's a negative current flowing. And now let me connect the 100 loop coil. And I'll start by moving the magnet in very slowly. You see a deflection to the right, pull it out to the left. And if I go in quickly, you see a much greater deflection. Okay, so the rate of change of the magnetic field affects the current also.
There is an illustration of induction. So we have an interaction between electricity, magnetic fields, and this is basically how a generator works. You move around a magnet and you know, obviously I showed you the turbine hall at the Snowy Mountains scheme. Okay, now this is a cathode ray tube. Now people here are enough familiar not with LCD displays but with the original TV picture tubes. And what the TV picture tubes was, they actually got an electron beam and scanned it across the front of the screen and built up images, I think about 50 of them per second, and that's how we got our old style TV screens working. And this is showing us that, remember I was saying, look, current flowing in a wire will actually interact with the magnetic field and you'll get a motor. This is sort of saying we have individual electrons being steered or deflected by a magnetic field. So that's another bit of phenomenon that's happened, and we did actually once upon a time use that for TV picture tubes. And that's mostly an obsolete technology these days, but I understand some aircraft still use cathode ray tubes because it's a hell of a thing to update the technology in a plane and get past the aviation regulations. Anytime you make a change, is it still safe, sort of thing. And then the aircraft companies crank out planes that have flaws in them and they crash accidentally and these sorts of things. So it's a complicated world, I guess you would say. Now, continuing the story, remember I showed you the original picture of James Clerk Maxwell. Now here is a statue in Edinburgh. So you might not be aware, but he's one of the grand figures in science in terms of the synthesis he made. And while I'm going to disagree with, I do respect the innovation and the thought that he put into it. Now, on the side of this statue, we do actually have Maxwell's equation. And I don't want to try to overwhelm you, but let me try to sort of tell some stories here. This one is the change in a magnetic field, and that generates an electric field which can push current through a wire. Remember we showed you that sort of thing with the guy pushing the magnet through the loop? So a changing magnetic field generates an electric field. And then this one down here, think of D. J is current and D is, I think, a variant on the electric field. A changing electric field makes a magnetic field. So those two things are linked intimately together. And when did I show you that a changing... Oh, well, basically, yes, I did show you, look, current generates a magnetic field. That was one of the first videos we showed you. And obviously you can change that to say, all right, changing electric field, moving particles, they also generate a magnetic field. But certainly current can generate a magnetic field. That's what that one's doing. He brought all those results that I was talking about and brought them under the same roof. And what he did as well, he actually explained radiation. Be that radio waves that we listen to the radio on, be it light from the fluorescent tube above, be it sunlight, if there was actually any sun coming in, or be them X-rays or gamma rays or whatever, they're all cut from the same cloth. And what actually happens is you have electric fields and magnetic fields cooperating. The changing electric field generates a changing magnetic field. The changing magnetic field generates a changing electric field. And they are coiled together like a pair of snakes. And let me try to show you. There is an illustration of what's going on here. That is the electrical and magnetic picture behind light, behind radio waves, behind X-rays and gamma rays, if we want to go that far. Obviously X-rays and gamma rays, people tend to think of them as photons, but let's not go there. Things are complicated enough the way we're going. And that is showing us how light comes from electricity and magnetism. Right? That is one of the stories we have from physics that perhaps you might not think. And also that radio waves, light, gamma rays, X-rays, they're all cut from the same cloth. Now, one consequence of this is that we have a magnetic field with an independent existence to the electric field that generated it at a point in space. Now, if you have a magnetic field and a charge moves through that, it experiences the force. But if you have a stationary charge and you move the magnetic field, Maxwell's theory has difficulty coping with that story. So, okay, now this is your moving magnet and conductor problem. And this is the thing, as I've said, because when you attach a magnetic field to a point in space, the ground shifts under your feet. What is happening to that point in space? Now notice here, it actually says at the bottom, and I'll read it out, this problem, along with the Fizeau experiment, aberration of light, and more indirectly the negative ether drift test, such as the Michelson-Morley experiment. Michelson-Morley experiment, quite hard to explain, I'll only be touching on that, formed the basis of Einstein's development of the theory of relativity. So Einstein is thinking, hang on, it's not the charge or the magnetic field, it's the motion of the charge with respect to the magnetic field that is important. And that was one of the things that Einstein keyed on. Thing is, Ritz also keyed on the same thing and came up with his own quite different picture. So so we have our problems. Now, another way of fixing those problems, remember that picture of Lorentz that we had from quite some time ago, and here we have our Lorentz transforms. Okay, I know formulas, and I hope it's not too overwhelming, but basically this line here is the crucial one. If we have a magnetic field that is moving, it will make a phantom electric field which will then move our particles. So there is balance. The Lorentz transforms take Maxwell theory and restore balance. But it was done in a quite unsatisfying way. And, you know, basically Lorentz just dreamt this up. Einstein, with relativity, turned things around. He said, look, let's assume that the speed of light is constant, and from that we can get to the Lorentz transforms, and from that we can sort of make electromagnetism work better. We will be getting to light in a moment. I am focusing on electromagnetics in its way. Now, while this approach was powerful, it had other problems. Now, notice that it attaches properties to a point in space. And as I said, when you're moving to a point in space, it's not anchored to anything. The ground is shifting under your feet. Now, what it also means is that theoretically there can be things called magnetic monopoles. That is a freely floating north pole without a matching south pole. And I guess it's hard to read this in detail, but, you know, some condensed matter, okay, what does it say here? Concept stems from particle theories, notice the grand unified and superstring theories which predict their existence. And of course you can say, well, maybe that's a good reason not to believe in those theories, but that's going off on quite a rabbit hole, I suppose. Also, this is getting a bit technical, but you also have advanced and retarded potentials attached to a point in space. So a point in space actually knows what's going on in the future. It's sort of one of the things that comes out of this theoretical perspective. Now, Murray has actually said, I may not be a physicist, but I at least do have a qualification. So I've absorbed a decent amount of physics along the way. And let me tell you, physics is like a very neat kitchen where as soon as you open one of the doors, all the crockery falls out, okay? That's my metaphor for physics. Physics is about approximation upon approximation, idealization upon idealization, dodgy mathematical hack on dodgy mathematical hack. And the amazing thing is that it all works at all. And I don't want to be too cynical. Physics is powerful, useful, that sort of thing. But it's a matter of whether you can get away with it in a given context. And here we have consequences, and here there are problems. So now, time to go to that alternative approach that Ritz put together. Now, his approach was to take our Coulomb equation and add to it ideas about velocity and acceleration between the charges. Because notice, you had Coulomb's law, and then you added velocity and so on via Maxwell's equations. But here, now if we go over here, here is the terms in the Coulomb equation, if you actually remember that far back. And all of these things are saying, look, there's velocity and acceleration interactions between our particles. So what Maxwell's theory added to the Coulomb equation is built in from the start. It has the equivalent of the Lorentz transforms built in right from the start, and you don't need to make these sort of adjustments. And no properties are associated with a point in space. All space does is give you a ruler, a way of measuring the distance. You don't actually say, here this thing, this generates a field, the field is in this point of space, that's associated with that point in space, and then that acts on something. Now, this is I guess a subtle distinction, but here it is actually significant and meaningful, I suggest. So how does Ritzian theory work? Now, it does actually say that there are subparticles that are projected from the particle over here, which flies through space and hit whatever. And the point is, because of that relationship, This flying subparticle or fictitious particle never leaves the shadow of the thing that it generated. So it's always got that built in. This is where I came from. These are the conditions where I came from. You don't sort of do that. Space only provides a ruler, only provides a dimension. As I say, Ritz said that they were fictitious particles, merely a different way of gathering together these relationships between particles and thinking about them. So I guess maybe you can push it too far, but for the moment, that's why it's called a ballistic theory. Now, magnetic fields by this thing no longer have an independent existence. They're an artifact, a convenient fiction. You can take this formula and manipulate it, and I won't do that now, but you can extract things that behave like the magnetic field, things that behave like the Lorentz transforms. You can, in fact, extract that from this. Ritzian physics, I say, encompasses all the effects that were drawn from to develop Maxwell theory. Coulomb's law, positive and negative charges, electricity being the flow of charges, moving charges, magnetism from moving charges, electromagnets, generators and cathode ray tubes. So they can explain all those things. Now, what is the one missing part? It's actually radiation, right? Now, if we go here, now, I will actually introduce this extract from a paper that was written by my uncle Zygmus Bedrikas, ex-professor of electrical engineering at the University of Western Australia. So I guess there's a family connection. That's why I've been exposed to these ideas at a young age. This particular thing is saying this result, which is sort of a Maxwellian type conception of radiation, we can actually derive that from Ritzian theory. We can take that formula I showed you and come up with radiation. So that's the one missing ingredient, and I think my uncle managed to derive this back in 1968. So you can see what we're doing here is we don't have the stepping stone of a magnetic field. Electric field makes a magnetic field, the magnetic field then continues to make the electric field. This is just saying all we have is our electric interaction, our particles wiggling up and down, and we can develop this and say, aha, we have a phenomena like radiation coming from this. We skip the step of ever actually having a magnetic field. As I say, you can derive the magnetic field and call it a convenient fiction or an artifact or whatever you want to say. Now, I've mentioned my uncle. I will also mention Robert Fritzius. He's someone who's also done work in this area that I've drawn from. Now I'm actually going to change gears a bit. Relativity focuses on light having a limiting speed and its consequences. Now, we've looked at the electromagnetic picture, which I think is very, very important. And if you watch any of those many documentaries on relativity, they just jump over all the electromagnetic toing and froing. And I think that's very important because it does actually provide some information. But anyway, so now I will go to a movie called Young Einstein. Okay? I don't know if anybody's seen the film Young Einstein.
I'm aware.
Okay, well, Young Einstein, a film by Yahoo series. And one of the things is Einstein is explaining, I think he's actually explaining it to a pretty young lady, but you know, those are the convenient things that happen in these films. And he's saying, look, if we have a clock, you know, with the hour hand and the minute hand, and we are moving away from that clock at the speed of light, time will seem to stand still because the clock doesn't change its position, because it takes the speed of light to get to us to tell us that the clock has changed its position. So I think relativity has problems, and but I am sort of trying to say that sort of thing gives us a bit of a flavour, a picture of where relativity is coming from. Now, there were some funny things going on with light, and it was actually hard to explain all of it. Now, one of the things is stellar aberration. Now, as the Earth moves through its orbit, depending on whether it's moving towards a star or away from the star seems to shift position. Okay, one funny thing that happens, right? Another thing is that if you send light through water, it will either be slowed down by the water or sped up. And so here's water flowing. You can see here the light travels through the water and picks up the speed from the water, and then this water is coming around, and there it's going against the flow of the water, and it slows down a little bit. And then when the light finally gets here, because there's a difference in the two speed of the light, it does actually look different. This is an interferometer, And here is Fizeau's interferometer, where he actually implemented this approach. Then you actually have the Michelson-Morley experiment. Now, I don't want to dwell on that too much, but you know how I was talking about the ambiguity between the magnet and the single charge. Michelson-Morley was a similar thing, except it was talking about light. And as I say, that's going down quite a rabbit hole to try to dig up the Michelson-Morley experiment. And there was also the thing that light seemed to be independent of the source. So that's obviously something that I disagree with, and maybe we'll sort of get to that. Now, Einstein said that the speed of light was constant, and physics looked the same regardless of who you are and where you were watching from. There was no privileged position to watch physics. Physics should always look the same regardless of how you're moving and where you are. Now, this had the consequence of the speed of light being an ultimate speed limit. Now, if you think about it, speed equals distance over time. If we're moving at 60 kilometres an hour, it means in 1 hour we're moving 60 kilometres. So if you say our velocity or our speed is fixed, that means distance and time must actually change as a consequence. So that's sort of saying, look, we said speed of light is constant, and then space and time change. And that's why space and time are changing. If you fix velocity, then something has to give. Now, as a consequence of that, force, mass, velocity and acceleration change too, but are advanced approaches using tensors. Hopefully we won't have to go down that rabbit hole. But, okay, speed of light is an ultimate limit. Now, let's take a look at that and start to introduce the Ritzian picture. Now, electron guns can't break the speed of light as you crank up the voltage. Now, electron guns are actually part of those cathode ray tubes, those TV picture tubes. So here we have right at the left-hand side, you generate electrons, they go forward and you put them across the screen and steer them with your magnetic field. And here's your acceleration voltage, and as you crank up that voltage, you cannot break the speed of light. I certainly agree with that. What you do with that observation is where we sort of get more complicated. Now, here's a graph that shows things. Now, C is called the speed of light, and you can see that basically if you pour more energy into it, I mean, this is in terms of energy rather than voltage, but let's not worry about that too much. So we pour our voltage in, and according to classical mechanics, we will break the speed of light. According to relativity, we pour volts, we pour energy in, and our speed approaches that of the speed of light, but it never actually breaks it. And that is certainly the case. But now, let's take a look at cannons, okay? Cannons, lovely little things. Now, one of the things about cannons, I'm going to jump between the speed of sound and 6 times the speed of sound, because cannons can actually fire their cannonballs faster than the speed of sound. And of course, bullets can also travel faster than the speed of sound. But one of the things about a cannon is that there is this speed limit of about 6 times our speed of sound. Not the speed of sound, but 6 times the speed of sound. That's because when the gunpowder goes off, it's very high pressure and very high temperature. In that environment, the speed of sound is 6 times the speed of sound. And that means the gas cannot keep up with the ball and push it any harder. This guy has actually made a transparent cannon, which I think is quite cute.
And the perfect fit. Right, let's film it in slow-mo with the Phantom Flex and see what it looks like. Here we go. Lighting the fuse. What a bang! Let's review the Phantom footage. Right, you can see me lighting the touch hole now. There it goes.
When you see this
plumes
video,
of black
you will
powder
see
smoke coming out of there.
Blast wave behind the cannonball, and then it will retract,
boom! It hits
and
the
cannonball
charge.
will keep going.
Look at that! You get the front
illustrates the principle that
it's
I'm
actually a
talking
front of
about.
flame, as those hot expanding gases are filling up that tube, propelling that ball out.
That is showing us how this speed limit happens in a cannon. Now let's look at whether they're cannons. Now we might observe that we can't get anything travelling more than 6 times the speed of sound out of a cannon. And we'd be wrong to say, oh, well that means nothing can ever go faster than 6 times the speed of sound. And that's the same sort of argument that we're applying to the electron gun. One of the things about rockets, and this is a bit of a physics subtlety, I hope you'll take my word for it, a rocket can travel faster than the speed of its own exhaust. Okay, so its speed builds up over time. Each little bit of stuff that goes off out the rocket. Now there is a limiting speed to how fast the propellant can come out of the rocket. It may not be 6 times the speed of sound, it depends on what's burning and how it's burning and so on. But there's going to be a limit there. However, the rocket can build up its speed over time. And whatever the speed of the exhaust, it can eventually travel faster than the speed of the exhaust. What are we observing between electron guns, rockets and their exhaust, cannons and so on? Ritz, relativity and experiment match up in their consequence. When you're talking about pairs of things, with multiple things change, you know, we are saying all roads lead to Rome. What we observe is a diminished acceleration. How we get there is negotiable. Now let's assume we have 2 shopping trolleys. We push one shopping trolley, it moves a certain amount, and then we push another shopping trolley and it doesn't go as far. Now why might that second shopping trolley not have gone as far? One reason is that we filled it up with cans of tomato soup. So when you push it, it's got a bit of resistance. The other one is we don't push it as hard. Don't pushing it hard, that's the Ritzian interpretation. Filling up with cans of tomato soup is a relativistic interpretation, but they both get to Rome. They both have a diminished acceleration. You just have a different path to that outcome. So then the next part of the story is relativistic velocity addition, and that's the other complexity. Now, let's assume you throw a ball, you can throw it at 20 kilometres an hour. Fair enough. Now, let's assume you're riding on the back of a ute or a pickup truck, and you throw the ball over the front. The ute's travelling at 20 kilometres an hour, you're throwing the ball at 20 kilometres an hour. Someone watching this situation will say the ball is travelling at 40 kilometres an hour. Okay, they add up. But if the speed of light was 30 kilometres an hour, you would be watching this and that speed couldn't break 30 kilometres an hour. It would be getting close, just like how the electron gun was getting close to the speed of light, but it wouldn't ever break. And that's relativistic velocity addition, which is different to just a pair of things. It's like 3 things interacting. And there you have a difference between Ritz and relativity. So one thing I will say is, look, there are experiments in particle accelerators which do suggest that there is relativistic velocity addition. But in my view, it's like the stage upon which the performers perform. There's always something in the background. It's the metal of the particle accelerator that forms this interface. Or, you know, don't push this metaphor too far, but you're watching the truck and we're all on the one road. So this basically links things together, and it makes it look like there's relativistic velocity addition while there's not actually relativistic velocity addition. Now there are some situations where I think you can, as it were, remove yourself from Earth. You can be separated from the particle accelerator and be doing your own thing. Now, so what I will try to explain it is, if we have our cannon firing out the cannonball and is limited to 6 times the speed of sound, and then that cannonball explodes, and let's say it explodes at like 3 times the speed of sound, then that fragment at the front will actually reach 9 times the speed of sound. So we push a cannonball out of the cannon and explode it, and one of these fragments will in fact break that. And you can actually say, look, this is something that is happening totally independent of what's going on around us. I guess the front fragment is like you're on the truck and you're throwing the ball and you're getting that extra velocity. So that's the thing with the cannon. But, you know, I do believe you can actually do an experiment with an energized beryllium nucleus. It's just about to explode into 2 helium nuclei. And if it is travelling at 99.75% of the speed of light, then one of those fragments will break the speed of light by 0.25%. So this is like the particle version of that cannonball story I told you. And I actually came up with this experiment, I don't know, 10 or more years ago, I forget. And I did actually write to the chair of the relativistic heavy ion collider in the US, and I didn't get a reply. So you know, the story of science is that, you know, all hypotheses are open to challenge, but let's just say that there's a certain degree of what you call it, privilege, or that's the word I'm looking for. But basically, not everybody gets taken equally seriously. On paper, physics is about the equality of challenge. You know, everyone can participate in science, everyone can challenge. The reality is, in order to effectively challenge, you need to have reputation. And it's hard to get reputation because it's other people who already have reputation who are the ones that grant your reputation. So, you know, it gets hard. But, so another way I can put it...
PhD will help.
Yeah, well, another thing I will say is what I did was I baked the cake according to directions and it didn't rise. And there you go. Something wrong with the oven, I suppose. Okay, so there was that one. So we've got that story with the nucleus. I've also had the story with the cannonball exploding. Now let's imagine we have some compressed gas that is expanding, okay? That compressed gas is moving at close to the speed of light and it's also expanding. So what's in front can actually break the speed of light. So a bit of compressed gas that is ejected and is still expanding. That's one way you can break the speed of light. Now these things are actually called interstellar jets. They come out of, you know, quasars and black holes, and you can see this picture here. They come out the axes top and bottom. And people look at these ejected things coming out of these very energetic areas. I guess they're areas where there's some really intense shit going on. So that is a technical scientific term, really intense shit going on in these active galactic nuclei. And you know, there's I think that's M87. And one of the things is, notice here is a picture of these wads of gas being ejected, and they're actually saying at the bottom there, you can see moving with a speed of about 6 times the speed of light. Now, the story from science was actually, well, if the thing is angled close enough to you, it will seem to be travelling faster than the speed of light, but won't actually. But then they did some further study and they found, well, the angles aren't actually that close. So if we go here, I'll read this one out. Some contrary evidence. Fizeau presented maps of arc-second resolution, which have revealed outer double structure in all but one of the known superluminal sources. An embarrassment is that the average projected size on the sky of the outer structure is no smaller than that of the normal radio source population. Okay, that's a bit of a gobbledygook thing, takes some interpretation. But then it says, in other words, the jets are evidently not, on average, close to the Earth line of sight. So basically, they have to be angled really close for relativity to kick in and make it look like they're travelling faster than light when they're actually not. But if the angle is like that, and they seem to be travelling faster than the speed of light, they probably are. So in this case, if it quacks like a duck, it probably is a duck. Now, how have they actually rescued this theoretical picture? They've actually speculated that the things might be coming out of the jet and going in a spiral. And if you think about it, if you watch a spiral for long enough, eventually there will be an angle that's just right compared to the Earth. Now, but I will also say this is basically grabbing for a resolution of this issue. Basically, if you go back to Ptolemy, he had epicycles. So we have planets moving across the sky and sometimes they go backwards. And Ptolemy had epicycles, so these planets actually operated on their own disks. And that is one of the cynical things you can say about a given scientific theory. It's generating epicycles. It's coming up with complexities that save things, while eventually we might look back and say, what a stupid idea, right? So that's the story with epicycles. You also might have heard of the saying Occam's razor, that things should be as complicated as necessary and no more complicated. So this is where I'm sort of saying, look, I did actually stick my neck out on that beryllium nucleus. If somebody had actually done that experiment, I would have to say, oh shit, relativity is right. But I thought through all the things and thought, this is one thing where if I observe that result, I'd actually concede to relativity. And similarly, if there is a detailed enough observation which shows us that there really is spiral motion, and it's not spiral motion which we hypothesize to save the theory, but we have other reasons for believing there really is a spiral motion, well, fair enough. But one of the things, if you look into these superluminal jets, the astronomers don't really know how they've happened. They don't understand the mechanism properly. There is not a good understanding of these things. And then they're basically saying, we've got a very rubbery understanding of this, but we know this must support relativity. So I personally think if you look at this whole story, it's a bit more rubbery than they would want you to believe. And remember, before they came up with this saving spiral idea, at the time they were saying, look, this is pretty embarrassing. It looks like these things really are travelling faster than the speed of light. That was actually what was said in those scientific conferences back then. So, now we'll lastly go to atomic bombs. And some people say, oh, look, the atomic bomb is evidence for relativity. Now, there is the reaction that takes place in an atomic bomb, or indeed a reaction. Notice the neutron comes from the left, it stretches out the nucleus, and then the two positive parts of the nucleus get blown apart. Now, think about this. What do we need for this to work? All we need is Coulomb's law. I showed you Coulomb's law before. Same size things repel and they are pushed apart. So let's imagine we have two positive charges connected by a string, and we go and cut that with scissors and boom, they get blown apart. That is Coulomb's law. You only really need Coulomb's law plus a few little add-ons to make an atomic bomb work. You don't need relativity. Now what you might say is, look, how much energy is this going to put out? Well, maybe not as Coulomb's law would say. Maybe we need to correct it. But remember I showed you that Ritzian formula with all the velocity and acceleration terms. I think it's quite possible that if there is a correction to be made, you could actually use the Ritzian formula for that. But another thing I'll say about atomic bombs is that atomic bombs have got a fudge factor, or in polite company we say they've got an adjustable parameter. Like, how much energy does a nuclear bomb put out? They make these theoretical calculations about the maximum energy, and then they actually measure the energy and then say, aha, the atomic bomb has a yield. So its actual energy output is somewhat less than the theoretical maximum. And you have this adjustable parameter or fudge factor called the yield to actually connect the things together. So to say that here is this atomic bomb, yes, it's giving out a lot of energy, but whether we have an accurate idea of that energy that points in the direction of relativity or any number of other things, and also we look at this picture and say, hang on, relativity? No, that's Coulomb repulsion. So that's sort of me challenging that story about atomic bombs. So now I've actually reached the end. Now one thing I have to say is that when it comes to the electromagnetic Lorentz transforms, I can actually develop some quite detailed mathematical theories. For pretty much everything else, I can at least tell a story about how what we observe is actually consistent with Ritzian theory. I recognise I can't do some sort of detailed mathematical story there all the time. I can at least tell a story about pretty much everything. And I think I've got a friendly audience here. I don't think you're going to be hostile. But I will say, look, if you assume that I'm onto something and relativity is flawed, assume that for the sakes of argument. It may well be that relativity is flawed, but relativity has had a hell of a head start, and I am one person. So please be realistic about what I am able to do. I have a life to lead as well as pursuing this as a hobby, and I'm not paid to do it, unlike a bucket load of academics all across the world. And I suppose that's maybe special pleading, but never mind, we all have to do it from time to time. So anyway, I am certainly happy to answer some questions. I hope they come from a place of interest rather than hostility. Anyway, thank you for listening to what I have to say. I do appreciate that.
And this is a very